Okay, today I want to talk about the problems of base rate. One of the things we do is we often look at numbers which require a more complex analysis, and we end up trying to use simplifying rules. So what I'm going to do in a minute is show you an example using a test for a disease called the XYZ disease, which actually will find or will be accurate 95% of the time, which means 95% of the time, if you have the disease, you will be detected. But 5% of the time, it will detect people as positive who don't have the disease. So we're going to go to the town of Albany with a population of 1,000. And here we know that one person in this town has the XYZ disease because the probability of having the disease is only 1 in 1,000. So 999 don't have it, while 1,000 do. So I make this a little bit of a decision tree. You can see here I have 1 and 999. One has the disease, 999 don't. So now let's imagine that you have the XYZ disease. No, I'm sorry, let me change that. Imagine you test positive for the XYZ disease. Now, this doesn't necessarily mean you have the disease because you could be a false positive. But what do you imagine the probability is that you actually have the disease? Now, if you're like most people, you would assume that you have a 95% chance of having the disease. That seems to be the logical and obvious answer. But the reality is, it's much lower. And what we're going to do now is do an analysis that shows you what the problem is when we look at these types of tests if we don't consider the base rate. And in this case, the base rate is one chance in 1,000 that you have the. Okay, here we go. So 1,000 people take the test. .95% accuracy of the test. But again, we have 5% that will test positive who don't actually have the disease. So here's how the calculation has to go. We take our 1,000, we recognize that one person in 1,000 has a disease in our town of Albany. But 999 do not. So the test is going to say that 950 do not have the disease because it's accurate, but it's going to say that 5% have the disease that do not have the disease. So that's going to be 50 out of 100 are going to have this false positive test. So what does that tell us about your chances of having the disease if you have tested positive? Well, what we have to do now is we recognize that actually we know that one person has tested, well, what we know is that one person will accurately test positive out of that 50. So let's illustrate that here in my tree form. So 49 do not have the disease, and one person does have the disease. So what's the probability of that one person? Well, in reality, it's going to be much lower than the 95% that you thought, because what this is telling us that in reality, is only 1 out of 49, or approximately 2%. That's only 2% versus the 95% that most people think. So what this tells us is that when you're looking at these types of situations, you have to look at the base rate. Many physicians and other diagnosticians will make exactly the same mistake. This is an example of Bayes' theorem, which we will talk about a little bit later on in the course. Thank you.